morning, everyone. So we'll start our class today with, I think, bridge rectifier. I will quickly explain bridge rectifier, and then we can move on to filter circuits. So bridge rectifier is another type of full wave rectifier. Uh, Here, instead of using a center tap transformer, like in the case of full wave rectifier, we are using a normal transformer that is one having a primary coil and one having a secondary coil, and without any center tap here. Right. So in this bridge rectifier, instead of using two diodes, we will now be using four diodes connected in this manner. If you look at this, so here load means it is same as writing load resistance. Okay, so when I write load, it means that this is a load resistance. Now, if you look at the circuit here, and here again in our AC input source, we have in India 230 volt peak voltage AC and 50 hertz frequency. And depending on the transformer number of turns in the secondary and the primary transformers, we have a certain value of peak voltage in the secondary of this transformer. So let's say the signal voltage is Vs and the peak voltage is Vm, and we can represent it using sine omega t. The alternating current signal, we can represent it using this trigonometric function, and Vm is the peak voltage here. So depending on the step down ratio, the transformer ratio here, the Vm maybe it could be around 4 volt, it could be around 5 volt, 10 volt, 12 volt, 15 volt, whatever we desire. Okay, then we connect the diodes like this. Now, during the positive half of the cycle, let's say, I think everybody knows by now that this is an alternating current signal Vs, and this is your omega t. And let's say, let me put a dotted line like this. And this is your positive Vm. This is your negative peak value Vm, Vp or Vm, whatever. And it's like this. So this is the positive half of an AC cycle. This is the negative half of an AC cycle, which I have discussed several times. And this constitute one complete cycle. So the next cycles are just the next wave are just a repetition of the previous wave in an AC signal. So during positive half of the cycle, let's say the upper side is positive, the lower side is negative. Now, if you have a positive side connected to the upper side here, now if you look at this circuit here, if this side is giving a positive voltage, here this is an N type, this is an N type, this is a P type. According to this diode symbol, this side is P, this side is N, this side is P, this side is N, and this side is P, this side is N. Now, during positive half of the cycle here, you will find that this diode D2 is under forward bias, and your diode D1 is under reverse bias. Diode D1 is under reverse bias in this case. And during this cycle itself, here you are having a negative signal here. So negative signal means this diode D3 will be under forward bias, diode D4 will be under reverse bias. Okay, so that means this diode can conduct current, this diode can conduct current, but this diode and this diode, they cannot conduct any current. They will be under reverse bias and no current can pass through it. Therefore, under such condition, you will find that a current will be flowing through this diode D2. Sorry, this arrow is wrong. So current will be flowing through this diode and current will be flowing downwards like this. And then as the current passes through this diode, it will flow through the load resistance from top to bottom, and it will flow along this line. And I say that this diode D3 is also conducting. That means the current will pass through this diode D3, and then it will go back to this circuit. That is during positive half. You will find that current flowing from top to bottom here across the load resistance. Now, when we consider the negative half of the cycle, that is between pi to 2 pi here, between pi and 2 pi, you will find that the lower side is under positive potential and the upper side is under negative potential. If that is the case, positive is now connected to this diode D4, the P type of this diode D4. So during the negative of the cycle, diode D4 will now be conducting. And when you connect the positive terminal to diode D3 will not pass any current because of the reverse biasing. And In that cycle, this side is positive, the upper side is negative, in the negative of the cycle. So when you connect a negative signal to this, diode D1 will be conducting because negative is supplied to N type of the PN junction. So diode D1 will be under forward bias and this will be conducting. And when you connect a negative voltage to the P type of this D2 diode, this will be under reverse bias, so it will not conduct in the negative of the cycle, so this will not pass any current. Now, if that is the case, you will find that this positive signal is connected to this diode D4, and this diode D4 is under forward bias and conducting. So current will flow from this, and it will flow through this diode D4. It cannot flow through diode D3. It will flow through this diode D4, and the current will pass from top to bottom during this cycle, and it will flow like this. The diode D1 is conducting, means via this diode D1, it will go back to the negative terminal here. Okay, so if you follow that current flow, like switching on and switching off a diode, that is forward biasing and reverse biasing of these diodes which are connected in this bridge form, you will find that during both positive half and negative half of the cycle, current will flow through this load resistance in the same direction. So you will find that if you measure the load resistance for output voltage across the load resistance as current passing through it into resistance of the load, then your output voltage will be something like this. Okay, between 0 to pi, pi to 2 pi. So during these two cycles, they will it will have a current from top to bottom. Therefore, we achieve what is called unidirectional flow of current. Unidirectional flow of current means this is a under forward bias. So if it is under forward bias, then sorry, for I misspoke that. So unidirectional flow of current means this is now a direct current. Okay, so instead of having alternating current which reverses its direction in every half cycle, you have unidirectional flow of current in both the cycles during the positive half of the cycle, that is between 0 to pi as well as pi to pi. Now, again, if you want to calculate all those DC current and all those AC current and all, this is how you're going to do. That is between 0 to pi, your this thing will be this. Now, the difference here is that in this bridge rectifier, you now have a true RF. How do we have a true RF instead of a single RF in bridge rectifier? So the bridge rectifier difference here is that by the introduction of two here. Thing is that when you are connecting two diodes like this, in one cycle, two diodes are under forward bias, two diodes are under reverse bias, two diodes are under forward bias, another two diodes are under reverse bias. So if two diodes are under forward bias, like let's say in the positive cycle, diode D2 and diode D3 were conducting, so current will pass through diode D2, and diode D2 will have a forward resistance of RF. This is the load resistance RL, and it passes through the load resistance RL, and then it passes through this diode D3 and then goes to the negative cycle, right? The negative terminal of the secondary of the transformer. So it passes through diode D2 and diode D3. Diode D2 has an internal resistance of forward resistance of RF, small resistance like we discussed before. Diode D3 also has a forward resistance of RF. They are both very small resistance. So the total resistance of the circuit will be like, the circuit will be something like, it will pass through a small forward resistance of the diode, and then it will pass through the load resistance RL, and then it passes through, this was diode D2 resistance. Now this is diode D3 resistance. It passes through diode D3 also. That also has a small resistance of RF, and it goes through the secondary of this transformer. This is how the circuit appears. The circuit will look like according to the current flow. It passes through diode D2 and diode D3, both are having forward resistance of RF. So what is the equivalent resistance of this circuit? Equivalent resistance is they are all connected in series, means RF plus RL plus RF. So it will be 2 RF plus RL. So other than that, this is the same peak value of voltage, and then you just put this thing, and I think you can continue the calculation. And usually we choose RL to be much greater than RF, so this is equivalent to writing RL. Then we can write your peak current as this, and then you can do the subsequent calculation same as the way we did our full wave rectifier, center tap full wave rectifier. Okay, so please complete the calculation. Uh, please complete the calculation. Just a minute. So these are very simple things. So you please see, try to recall what we discussed. Hmm. Okay. Now, let us define this quantity, the peak inverse voltage. So the peak inverse voltage is the peak voltage appearing across the diode during the reverse or negative cycle. During the reverse bias or during the reverse bias condition, what is the peak voltage appearing across the diode? That is what is defined as the PIV, peak inverse voltage. So in a full wave, in a half wave rectifier, remember, in a half wave rectifier we have a primary and secondary of this transformer, and this secondary of the transformer has a signal voltage of V is equal to Vm sine omega t. Now you have a load resistance RL, you have a diode D1 here, single diode here in a half wave rectifier. So this was your half wave rectifier. So you will find that during the positive cycle, this diode is under forward bias and current can pass through it. Now, during negative cycle of the input signal, this diode will have the polarity of the secondary coil will be something like this, and this diode will be under reverse bias. This diode will be under reverse bias. So under reverse bias, the diode D1 cannot conduct any current. Diode D1 cannot conduct any current. That means there will be a certain voltage. What is the peak voltage appearing across it? If the diode D1 cannot conduct any current, so under reverse bias, it will be something like this. So current, no electrical conduction means there is an insulation here. Current cannot pass through it. So this is RL. This is your secondary. V is equal to Vm sine omega t. Now we know that during this is positive half. During this negative half, this diode cannot conduct any current, but the voltage appearing across the diode is varying like this. The voltage appearing across the diode is increasing in this direction, and it reaches the peak value Vm and then goes back to zero. The voltage that will appear across this diode will be increasing in this direction and in the reverse direction, and then goes back to zero. So if the diode cannot pass through any current, there will be a certain reverse voltage applied across the diode. That's what I mean. There will be a certain reverse voltage acting across the diode. So this diode, this voltage, the peak value of such voltage is called peak inverse voltage. The peak value of such voltage is called peak inverse voltage. We will talk about in the next section. We will talk about, later on I'll talk about avalanche breakdown and reverse breakdown. The thing is that when you see, it's like connecting this during this cycle, diode is under reverse bias, means, let me write something here. Where is the blank page? Yeah. So this is diode. Let me look, return to this figure once again. Now, if you connect this diode to, let's say, a DC signal like this, when you connect it like this, this is under reverse biasing. So this is what we are just looking at, because under under in this negative cycle, diode D, this diode D will be under reverse bias, right? And the voltage appearing across this diode is increasing and decreasing like this. So it's like equivalent to writing that the voltage, the reverse voltage. So this is your forward current, this is your reverse current, this is the reverse voltage, this is the forward voltage. So the forward side we already explained it, and the reverse side we say that it allows only microampere current, that is very small current. Okay, now when you connect under reverse bias, you are allowing, see, there are minority holes here, majority electrons here, and here there are majority holes, and minority electrons. So under reverse bias, minority holes will be injected, minority holes will be conducting across this diode, and minority electrons from the inside also will be moving towards the n side. Minority electrons from the p side will also be moving towards the n side. When you connect the negative voltage to this p type here, minority electrons from the p side will move towards the n side. Now, if you increase the reverse voltage, this is the zero voltage, and if you increase the reverse voltage along this direction, as you increase the reverse voltage along this direction, these minority electrons and minority holes, which constitute our reverse saturation current, we talk about this reverse saturation current, which constitute the reverse saturation current, will continue to flow through it. But since the amount of minority electrons in the p side and minority holes in the n side, they are of very less number. Since the quantity of minority charge carriers are of very less number, even if you increase the reverse voltage to a large value, the current in the reverse direction cannot increase. It will be around 10 microampere or something like that, very small current. So the current cannot be increased beyond 10, 15, 20 microampere under reverse bias. Okay, under reverse bias, the current cannot increase beyond that because the minority charge carriers which contribute to this reverse saturation current is very small. Here, if you remember the diode equation, we talk about the current across the diode as minus of Is under reverse bias. Okay, this current is negligible. Therefore, we say that current is not allowed to pass through the diode under reverse bias. That's how we conclude it, because of this very small quantity of the minority or reverse saturation current, which is about 10-20 microampere only. Now, if you continue increasing the reverse voltage, what happens is that even though the quantity of electrons and holes, minority electrons and holes cannot increase now, the increase of reverse voltage will result in acceleration or increase of kinetic energy of electrons. So if you increase the reverse voltage, if you increase further the reverse voltage along this, kinetic energy of these minority electrons will continue to increase. So if the electrons are moving with such a high kinetic energy, in the depletion region, when electrons are injected from the p side, that is minority electrons are injected from the p side towards the n side with a very high kinetic energy, with a very large high kinetic energy. Electrons, when it collides with atoms here, when it collides with atoms in the depletion region, electrons will transfer some of its kinetic energy to those atoms through inelastic collision. So when it transfers a large quantity of energy to atoms in the depletion region through inelastic collision, the atoms will now gain very large amount of energy. So when it gains large amount of energy, the amount of energy gained by such atoms might be sufficient, not might be, will become sufficient to break the covalent bonding. Okay, so let me repeat. Under reverse bias, we know that the current across the diode is due to the minority electrons on the p side, minority holes on the n side, and the concentration of minority electrons and minority holes are very, very less. So because of that, the current as a result of minority charge carrier conduction is very small, around 10-20 microampere only. And such a small current is what we call it as a reverse saturation current. Now, with the increase of this reverse voltage in this direction, those charge carriers, that is free electrons, minority free electrons, minority holes, will gain their kinetic energy, will have increase in kinetic energy because of the potential energy, reverse potential energy supplied from this potential source. So as they gain more kinetic energy, in order to pass through this depletion region, they will undergo a lot of inelastic collision with the atoms in the depletion region. So when it collides under inelastic collision, that is transfer of energy will take place, and when sufficient, like when you increase the voltage to a very large value, the reverse voltage to a very large value, the amount of kinetic energy transferred, to those atoms in the depletion region will now be sufficient to result in a breakdown of covalent bonding. So when such breakdown of covalent bonding occurs, it will be like electron is moving, it collides with an atom. So when it collides with an atom, breakdown of covalent bonding will result in release of extra electron in addition to the already existing electron. And under the action of this reverse voltage, these electrons will continue to accelerate. So as they continue to accelerate, they will collide with another atom, and they will result in formation of breakdown of covalent bonding, and they will result in formation of another free electrons like this. And as they move further, they accelerate again, they collide with another atom, and that will also result in a release of free electron, collide with another atom, release of free electron like this. So in this way, you will find that single minority electrons highly accelerated under this reverse voltage, high reverse voltage, will result in release of large quantity of free electrons, and that will result in large electrical conduction across this diode. So when you have a large current across this diode, the heat generated by large current through this inelastic collision will be sufficient to break down this diode, and that process is called avalanche breakdown. When you multiply free electrons like this through collision, the process is called avalanche breakdown. So when avalanche breakdown occurs, large current will result in damage of this diode. It will burn the junction. So when you have under reverse bias, when you multiply this free electrons through this avalanche process, that is inelastic collision, release of another electron, inelastic collision, release of another electron, and the subsequent steps as I describe here using this picture. So that will result in very large current, and that very large current will burn the PN junction. It will cause lots of heat, and it will burn the PN junction. Okay, it will damage the PN junction totally. So then the current in the reverse direction here, it will jump like this. Under such avalanche breakdown, the current in the reverse direction will jump like this. So that will cause large current. It will totally burn the PN junction. It will totally destroy your device. Okay, if you apply a very large reverse voltage. So what I mean to say is that depending on the design or the fabrication of this diode, different diodes will have certain uh, reverse voltage that can be accommodated, or the reverse voltage that is variable. Beyond such reverse voltage, the diode will burn, the diode will be damaged. Okay, so what I mean to say here is that you cannot apply a very large reverse voltage. There has to be a certain value of reverse voltage up to which you can apply. Only then you will prevent your device from breaking down. Only then you will prevent your device from breaking down. Okay, so here the peak inverse voltage is related to such breakdown. So here, this, as you see, under reverse, during this cycle, this diode is under reverse biasing, and the voltage appearing across this diode is increasing from, reverse voltage appearing across this diode is increasing from 0 value to Vm peak value along this line, and then decreases back to 0. So in your design, you should use a diode, or you should use your transformer. You should design a transformer such that the peak inverse voltage does not cause avalanche breakdown in the PN junction here. Okay, so your step down transformer should be such that it will be able to step down the voltage. It should be able to step down the voltage to such a low value that the peak voltage, the peak inverse voltage appearing across the diode is below the avalanche breakdown voltage. So the design has to be such that you have to be able to step down the voltage using a transformer, so that the peak voltage that will appear across your diode, the peak inverse voltage that will appear across the diode, is below the breakdown voltage of the diode. All right. So in designing this kind of electronic circuit, it is important to know the specification of the diode. What is the breakdown voltage of that diode manufactured by like from whichever company you purchase from? Okay, so the big inverse voltage is Vm here. Now if you look at this full wave rectifier, which what is that? Yeah, here if you look at this center tap transformer here, the Vs is Vm sine omega t, Vs is another Vm sine omega t. So during the negative cycle, that is, this side is positive, this side is negative, this diode D1 is under reverse bias. If this diode is D1 is under reverse bias, what is the peak voltage appearing across this diode D1 under reverse bias? The peak voltage is here. The peak value is Vm here. For this, between this interval, the peak voltage is Vm. Between this interval, the peak voltage is Vm. So if you reverse bias this under this negative cycle, the peak value of voltage that will act on this diode D1 will be 2 Vm. So by looking at the picture, I hope you can understand. So the peak voltage here between 0 to the midpoint to this upper side is Vm side Vm. The peak voltage between this midpoint, that is the 0, the reference voltage with respect to this lower side of the transformer secondary winding, is also Vm, another peak voltage. So under negative cycle, the lower side is positive, the upper side is negative. So this diode D1 will be reverse bias. So if this diode D1 is reverse bias, now if you look at the circuit connection is like this, is connected like this. The circuit connection is like this. Let me draw it. I think it would be better if I draw it. Under reverse bias, if you have a diode D1 and diode D2 is conducting, means it will be totally passing through this good conductor. So you can assume that there is a diode, another diode D2, but diode D2 is forward bias under negative cycle. If it is forward bias, then it will pass through it. The current will pass through it. It will be appearing like a good conductor. So this is what we call it as a Vs signal, Vm sine omega t, and this is another Vs is equal to Vm sine omega t. So what will be under reverse bias? What will be the peak voltage that will be under the peak voltage that will be acting across this diode D1? So the peak value of voltage between this interval is Vm. The peak value of voltage between this interval is another Vm. So you will find that the peak voltage that will be appearing across this diode under reverse bias, that is peak inverse voltage, should be 2 Vm. So the peak inverse voltage in for center tap transformer, as you see, it could be quite large. The peak inverse voltage could be quite large. So in designing a center tap transformer, we should take necessary care that this peak inverse voltage does not cross the avalanche breakdown condition. So if you increase the reverse voltage in this direction, and if your peak voltage, peak inverse voltage is something like between these two, let's say this is 2 Vm. If your peak inverse voltage is 2 Vm, and the avalanche breakdown can occur at this point. So if your peak inverse voltage is so large that it is even greater than the avalanche breakdown, it will definitely cause breakdown of the junction, and this diode D1 will be burned. Okay, it will burn because of the large quantity of free electrons generated under avalanche process. And under such avalanche process, once you generate large quantity of free electrons, then large current will pass through it that will generate lots of heat across the p-n junction, and the heat generated will completely destroy your p-n junction diode. So I hope you can see that under this center tap configuration, the peak voltage that will be appearing across the diode under reverse bias will be Vm plus Vm, that is 2 Vm. So we should take like special care if we are going to design this center tap transformer or rectifier. You have to design such that the peak inverse voltage is less than 2 Vm is less than your avalanche breakdown. 2 Vm is less than your avalanche breakdown. Okay. Now in bridge rectifier here, you will find that the peak inverse voltage is simply Vm, because here you are not having any center tapping here. So the signal appearing across this secondary of the diode, signal appearing across the secondary of this transformer is Vs equal to Vm sine omega t. So your Vm is the reverse voltage that will appear across your diode, D2 or D3 or D1 or D4 under reverse bias. You cannot have any peak inverse voltage greater than Vm. Okay, so therefore here in the bridge rectifier, peak inverse voltage is Vm. In center tap it is 2 Vm. In half wave it is Vm. Okay. So usually in practical rectifier, people go for bridge rectifier because here it is easier to prevent avalanche breakdown under reverse bias. Okay. However, in center tap, we have to have a very high quality p-n junction diode in order to avoid reverse breakdown, avalanche breakdown under this peak inverse voltage. When the peak inverse voltage crosses the breakdown voltage, it will undergo avalanche breakdown. It will burn your diode. So in most practical circuits, the design normally used is bridge rectifier, the one shown here. Okay. So please complete the calculation. It's same as your full wave rectifier. The only difference is you are introducing 2 RF here, like I said before. So I was thinking of teaching you the filter circuits and all, but I think that concludes our lecture because I have less than 1 minute now. If you have typed your attendance, I think we can exit the meeting. Okay.